Okay, thanks for the introduction, and good morning to everyone in America, and good afternoon for the ones in Europe, or even good evening in Asia. So I'm very glad to have this opportunity to present you my work. So thanks to the organizers. I want to stress that I'm much more a cosmologist actually than a specialist of quantum field theory. So I had to learn many things for this project, which is a small part of my PhD actually. And listening to the talks here, I'm realizing that I'm still clearly an outsider in this topic. So it's really a challenge to be here. I'm very glad to have any comments that you can have from the QFT point of view, for example. So indeed, this seminar is about stochastic inflation, which is this way to describe the large-scale fluctuations during inflation in a classical but non-deterministic way. So instead of a homogeneous background, we will describe the probability density function of our large-scale scalar fields. So this is the outline of my talk. I will begin by very briefly reviewing what is the standard approach to inflation and small quantum perturbations, and then go into the heart of stochastic inflation and the concepts that go with that. Then I will end up with some recent works that I did with my PhD advisor and a collaborator about extending the stochastic formalism to multifield inflation and a curved field space. So first, the standard approach. So of course, the whole point of inflation is to have this co-moving Hubble radius AH-1 that is decreasing. That is the main difference with the more usual radiation and then cold dark matter dominated eras. The important implication of that is that the large-scale fluctuations that we observe in the CMB were once inside the horizon. So they have a microscopical origin, and on these so-called sub-horizon scales, we can use what we know of quantum field theory in flat spacetimes to define the initial conditions for these seeds that will then give rise to the anisotropies in the cosmic microwave background. So the usual way to get inflation, let's say the simplest way, is to assume that there is a single scalar field that is both driving the background. So you have a homogeneous background, as often in cosmology, and you have this slow roll dynamics of the background in the simplest cases. But you also allow to have some small perturbations on top of this homogeneous background. And by quantizing those fluctuations, and for this there is a well-defined procedure which amounts to choosing the so-called Bunch-Davies vacuum in the sub-horizon region, you end up with some predictions for those fluctuations. So you have both classical dynamics at the level of the background and quantum dynamics, let's say quantum initial conditions at the level of linear fluctuations. And with those two ingredients alone, you derive this very famous result that the curvature perturbation at the end of inflation should be almost scale invariant, which is actually what we observe in the CMB. So this is why inflation is so successful. So let me go into the heart of what is stochastic inflation. So the idea is that it may happen that the potential is so flat that actually the quantum kicks can eventually dominate the classical drifts from the derivative of the potential. And even if at each time step, the quantum fluctuations are still smaller than the drifts, these quantum effects can accumulate over time and backreact on the large-scale dynamics. So actually, this process that we are describing here is a very well-known process in physics that is diffusion. And in order to take this into account, we'll have to give up on the fact that the background is homogeneous and to allow for large-scale fluctuations of our scalar field and therefore of our space-time. So the idea now is to divide our scalar field into infrared and ultraviolet sectors with large-scale fluctuations in the infrared sector and small-scale fluctuations in the UV sector. What we will do is that we will allow the large-scale fluctuations to be large, so we will treat them non-perturbatively, but we'll still assume that they come from microphysical scales where there were still small perturbations. So actually, let us have a more detailed look at this theory. So what we have to do is to define what is our infrared sector and our ultraviolet sector. So for this, we have to define a cutoff, of course. So we define this cutoff in Fourier space with the only available physical scale during inflation, which is actually this co-moving Hubble radius, which is decreasing. So what we do is that we define the cutoff scale to be slightly larger than the horizon size, this AH-1, in order to be able to use this feature of the fluctuations during inflation that they classicalize above the horizon. I will come back to this. So we have this cutoff scale that we define with this parameter sigma, which is just a small parameter such that the infrared sector is well above the horizon. And you see that when time passes, what happens is that you have the physical scales that are stretched above the horizon and then above the cutoff scale, such that they eventually join the infrared sector. So actually, I'll do it just once again, the infrared sector is growing with time because it receives new contributions from the ultraviolet sector. So if we want to describe the infrared sector, what we are actually describing is an open out of equilibrium system. So what is the usual way to derive the equations that derive this dynamics? The simplest way is just to kind of very simply divide your scalar field fluctuations in Fourier space by introducing a very sharp step function that selects only the modes that are above the cutoff in physical space, so in Fourier space that have a k smaller than the cutoff. Of course, the point is that during inflation, this cutoff scale is decreasing, and this is why we have this open system for the infrared modes. So when you plug this into the equation of motion for the full scalar fields, what you end up with for your infrared sector is not only the classical drift as we had in the case of the homogeneous background in slow inflation, but we also have a correction that comes from the time derivative of this window function. And as you know, the time derivative of a simple step function like this looks like a delta function. So the role of this new term in the equation of motion will be to select the Fourier modes that are actually evaluated at the time of at the scale of the cutoff at this particular time. So what I want to stress now is that this new term can be understood as a noise. So far, this psi term we just found it was looking like this when plugging the ansatz for the infrared and UV modes into the equations of motion. But now I want to stress that it can be interpreted as a classical random noise. So actually, if we are rigorous, this term psi should actually be a quantum operator. And this is because our Fourier modes should be quantized, and by being quantized, I mean simply developed in these annihilation and creation operators with some mode functions that multiply each of them. But the point is that we exactly defined the infrared sector to be the one that is on scales much larger than the co-moving horizon. So what happens is that on those scales, we can have this simplification that the quantum field classicalized, and there are ways that are much more rigorous to show this than what I'm actually describing here, having very simple arguments. But for example, you can look at these mode functions at the cutoff scale k sigma, which is selected by this delta function here. And when you look at the typical values, I mean, the typical expressions for this massless mode functions during inflation, you can see that on the super horizon scales, they converge to a real function. So these imaginary functions converge to a real function on the super horizon scales. And therefore, you see that this complex conjugate is nothing but the mode function itself. So what does it bring as a simplification? Well, simply, you can factorize this mode function, and the only operator that you are left with on the super horizon scales is actually not A and A dagger independently, but just the sum of the two. And you can define B, another operator that would be the sum of the two. And because it is expressed in terms of A plus A dagger, of course, it is its own Hermitian conjugate, so it's a Hermitian operator. And it is the only operator that remains on the super horizon scales. Therefore, it commutes with itself and with any other operators on the super horizon scales, hence the loss of the quantum feature of the system. So anyway, we can write simply what is this phi on the super horizon scales. It is this mode function times some operator B, and we know the statistics of B from the ones of the creation and annihilation operators. And what we find is that B has zero mean and some non-trivial two-point function. So this is a Gaussian operator. And therefore, we can now derive what is the statistics of this operator psi phi. And we find that it is a white noise because it is uncorrelated in time. It has also some spatial correlation. And of course, an amplitude that is dictated by the amplitude of the polar spectrum of the linear fluctuations. So the ultraviolet fluctuations, the one that are on the subhorizon scales, when they reach the cutoff scale and join the infrared sector. So all this is very intuitive. You have the power from the small scales that then gets transmitted to the infrared sector. So this equation, actually, I should have stressed, sorry, is the famous Langevin equation, right, with this stochastic noise. So now what I want to show is that from this Langevin equation, you can get the so-called Fokker-Planck equation. And I just rewrite the Langevin equation as the amplitude of the noise times a normalized centered Gaussian variable psi. And in general, during inflation, if you have some massless fields, the amplitude of the noise will be simply this h over 2 pi. So now you can derive this equation for the probability density function of your infrared sector, which is called the Fokker-Planck equation. So you have the time derivative, which is equal to some gradient terms and some diffusion term. And the drift comes from the derivatives of the potential. So this is the classical evolution of your infrared sector. And you have the diffusion with quantum origin. You see clearly the amplitude of the noise that is here that adds on top of this classical dynamics. I also want to stress the possibility to have this noise-induced drift coming from the ambiguity of the discretization procedure of these stochastic differential equations. This is something that I worked a lot on in the context of inflation. I don't have so much time to explain it, but I'm happy to answer questions if there are. And so from this Fokker-Planck equation, what we derive is typically this evolution for the probability density function. You have the convection that drives you towards the minimum of the potential, and the diffusion that makes you go in other directions. So now I want to stress a few applications of this Fokker-Planck equation. So there would be some applications in the inflationary universe, and actually I'm really interested into that, but I don't have the time to present all of this. But I want to focus instead on the possible applications for the purpose of this workshop on quantum field theory in de Sitter spacetime. In that case, the Hubble parameter is actually a constant and becomes independent of your scalar field that you simply take as being a spectator scalar field. And then you can derive very important non-perturbative results in de Sitter. And this is really the strength of the stochastic approach. So you can look, for example, at the equilibrium probability density function of your scalar field by putting this derivative to 0. And what you find is that the PDF is proportional to this exponential minus v over h4. And you see clearly that if the potential is something else than a quadratic potential, you will have very large deviations from the Gaussian case, which is what you would expect in a perturbative framework. So in particular, I want to have a look at the lambda phi 4 theory that we like to look at in the Sitter spacetime. And actually, we can derive what is the 1-point and 2-point functions at some orders in these parameters, which is lambda times n. And I should have stressed that n here is the number of e-folds during inflation. Sorry, this is has been for a long time that I'm using it. It is a time variable, which is well defined in stochastic inflation, the number of e-folds of inflation. So we can derive this kind of result where we find this very well-known infrared divergences for our scalar fields in de Sitter. And we have also the corrections that come from one loop effects that you can compute also in quantum field theory. This is the stochastic calculation, which is actually much simpler than the one loop QFT computation. So now I want to stress in the remaining 3 minutes a few recent results that we were able to derive in the context of multifield inflation and curved field space. And so first, the context is that inflation may well be driven by a single scalar field, but there is no particular reason for that. There may be many scalar fields actually during inflation that may be dynamical or not, that may be very massive or very light. They can have any kind of potential interactions or also kinetic interactions via this so-called field space metric that you can interpret as being a curved field space. So I want to put myself in this very general context and try to derive what is the stochastic formalism for these extended models of inflation. So what we did in this paper 2 years ago, but actually it was a very long-term project, was to derive the stochastic equations for multifield inflation with use of this Schwinger-Keldysh formalism for cosmology. So the point, of course, is that in cosmology, we are not computing in-out scattering amplitudes like in particle physics, but we want to compute these in-in correlation functions. And actually, I'm very glad to talk right after Professor Hu, from which I learned, from his book and his papers, I learned a lot about this. And so the idea is that you have these 2 branches of integration, one that corresponds to increasing time and one that corresponds to decreasing time. And one way to deal with that is to double the degrees of freedom in your path integral. And this is what we did. So we looked at the path integral over our fields that are both defined on the plus and the minus branch. And what we did is that we derived what is the effective field theory for the infrared modes, so the coarse-grained scalar fields, when we integrate out the small scale fluctuations. So you see this integral over the small scales, the UV fluctuations, we just performed it explicitly. I'm saying just, but it was quite difficult. And what we found, of course, as always in this kind of setups, is that we recover the classical action, which is actually in the context of inflation, this slow roll dynamics, and also an influence action that once you introduce these auxiliary fields, do this Hubbard-Stratonovich transformation, you can interpret as being a noise term in the equation. So all in all, we were able to derive these multifield Langevin equations. And also something that I should have stressed is that we worked also in phase space, which means that we also consider the momenta of the scalar fields to be dynamical quantities. So I don't have the time to present all the results. My time is already off. I just want to say that what we, again, with this formalism compared to the more naive one that I presented at the beginning with a sharp window function in Fourier space, is that we have a more consistent and rigorous formalism for deriving the equations. We control what is the approximations. For example, in principle, it would be possible to derive the next order corrections with this formalism. And also, we are able in this paper to solve the problem of covariance of the equations that we had discovered was always present actually in stochastic inflation due to this ambiguity of the time discretization. And I just want to finish by showing you this equation that I find very, very nice, which is the generalization of the Fokker-Planck equation that I showed you before to multifield inflation with any number of scalar fields with a curved field space. You see the field space metric here. In phase space, you have not only the scalar fields, but also the momenta. And very importantly, we have the appearance of these covariant phase space derivatives that we had to define and that we found the formalism was covariant with respect to those derivatives. So I will stop here. And if you have any questions, I'm happy to listen.
Okay, thanks for your very nice talk. And well, it's time for questions or remarks. So someone in the audience. Or in the chat. Okay, may I ask a question? Well, and indeed a question, because you have applied all your words in the sitter. So I wonder whether you can say something extra about the stability or instability of the sitter space according to all these new ingredients. So.
I don't think so, because of what you just said, that the results were assumed to be in de Sitter. So we didn't, I mean, we can't look at the back reaction of those scalar fields on the spacetime. However, there is the stochastic, I mean, stochastic inflation is about applying the stochastic formalism to inflation, where the spacetime is quasi de Sitter. It's not exactly de Sitter.
Yeah.
And then the formalism can be applied actually consistently also. And I didn't stress that a lot in this presentation, but actually many important non-perturbative results can be derived during inflation thanks to this formalism.
Okay, then, okay, thank you very much for your talk.